Hello and welcome to our second lecture. This week we will talk about intervals, Cartesian coordinates, functions, and sigma notation. First, we start with intervals. What is an interval? An interval is a subset of the real numbers which satisfies two rules. Rule number one, the subset must contain at least two numbers. And rule number two, this subset must not have any holes in it. So for example, the set of all real numbers x such that x is strictly greater than 6 is an interval. In this picture, I've drawn the interval in blue. Note that because the number 6 is not in the set, we draw an open circle at 6. The set of all real numbers x such that x is between -2 and 5 is an interval. There's more than two numbers in this set, and the set doesn't have any holes inside it. Because -2 and 5 are both in this set, we draw a filled-in circle at -2 and at 5. Here's another subset, the set of numbers x such that x is a real number and x is not equal to 0. The picture looks like this. It's all of the numbers except 0. This set has a hole in the middle of it, so this is not an interval. We can classify a finite interval as either closed, half open, or open. It's closed if it contains both of its endpoints. It's half open if it contains one of its endpoints but not the other one. And is open if it does not contain its endpoints. Here are some examples. Let's look at the first one. The set of all numbers x which is strictly between a and b. This is an interval. The endpoints are not in this interval. So in the picture, we can draw open circles. This is an open interval. We have a nice notation for this. It's curly bracket or rounded bracket a comma b round bracket. Next, let's look at the second one. Square bracket a comma b square bracket. This means a set of all real numbers x such that x is greater than or equal to a and x is less than or equal to b. This is a closed interval because both of the endpoints of this set are contained inside the set. Half open intervals are intervals where one of the endpoints is in the set and the other endpoint is not in the set. For example, square bracket a comma b round bracket is a half open interval, and round bracket a comma b square bracket is also a half open interval. We can also talk about infinite intervals, intervals which go all of the way to infinity or to minus infinity or both. An infinite interval can be closed or open. It's closed if it contains a finite endpoint, and it's open if it's not closed. But there's one exception to this rule. In order to make more advanced topology work, we need to say that the whole real line is both open and closed. Some examples. First of all, round bracket a comma infinity round bracket. This is an open interval because a is not in this set. Square bracket a comma infinity. Round bracket is a closed interval because a is in this set. And we have the same ideas for going to minus infinity. The bottom one, round bracket minus infinity comma infinity. Round bracket, that's another way to say R. That's the whole real line. And using this exception to the rule, this is both open and closed. We can combine two or more intervals together using the union notation that we talked about last week. For example, square bracket minus 8 comma minus 2 square bracket union square bracket 2 comma 8 square bracket is the union of these two intervals, and I've shown it here. This is not an interval itself because it has a hole in the middle. This is the union between two intervals. And that's enough about intervals. Let's move on to talking about Cartesian coordinates. Hopefully this chapter is revision for you. Hopefully there's nothing new here. We can describe the position of a point in two-dimensional space using two numbers. For example, the point P we can describe using the coordinates 4 and 3. This means if we start at this point, which is called the origin, 4 tells us we go right 4 and then we go up 3. Or if we want to describe the position of the point Q, starting at the origin, we go left 2 and then up 4. To show that we go left, I'm putting a minus sign in. This is minus 2, 4. The blue line is called the x-axis, and the red line here is called the y-axis. The set of all of the points x, y, where x is a real number and y is a real number, is called R squared. X is a real number. Y is also a real number. So you might think of this set as RR, or R multiplied by R, or R squared. This number tells us the dimension of our space. As I said on the last slide, the point 0, 0 is called the origin. For example, let A be the point 2, minus 1, and B be the point 3, 1. Draw the triangle OAB. Here it is. To get to A, we go right 2 and then down 1. This is the point A. To get to B, we go right 3 and then up 1. This is the point B, and the origin is the point O. Connect these 3 points together, we have the triangle that we're asked for. Draw the region of points which satisfy x is between 1 and 3. First of all, let's look at the left part. Let's just look at x is equal to 1. This is a vertical line. Y can be any number, but x has to be 1. So we have a vertical line just here. Look at the right side. Let's look at x equal to 3. This is another vertical line. Y can be any number, but x must be equal to 3. We have this vertical line just here. So the set of points that we asked for, x between 1 and 3, y can be any number. It must be this vertical strip which goes all of the way down to minus infinity and goes all of the way up to infinity. Draw the region of points which satisfy x is between 1 and 2. y is between 1 and 3. And it looks like this. X is between 1 and 2, so somewhere between these two lines. Y is between 1 and 3. Here's y is 1. Here's y is 3. We must be between these four lines, so we must have this rectangle. We can measure or we can calculate the distance between 2 points using Pythagoras. Look at this triangle. The base of the triangle is the difference between x2 and x1. The height of the triangle is the difference between y2 and y1. So the length of this hypotenuse, which I'm writing as double line P1, P2 double line, we can calculate the square root of the base squared plus the height squared. Or to say it another way, the distance between the point P1 and P2 we can write as double vertical line P1, P2, double vertical line is the square root of x2 minus x1 squared plus y2 minus y1 squared. For example, the distance between the point 1, 3 and the point 4, minus 1, we can calculate by putting these numbers into the formula, and I'll leave it for you to check that we get 5. Next, I'm going to talk about functions. I'm going to be writing y is equal to f of x. Here, f is the function, x is the independent variable, and y is called the dependent variable. What is a function? Precisely, a function from a set D to a set Y is a rule that assigns a unique element of Y to each element of D. The set of all the possible values of X, that's all the numbers that we put into the function, is called the domain of F. The set Y, the set of dependent variables, is called the target of F. Inside the target of f, we would have the set of all of the possible values of f of x. This is called the range of f. We can write a function like this. If we have a function which maps from domain D to target y, we can write f colon d arrow y. So for example, I might be interested in the function f, which maps from the real numbers to the real numbers, and which has the formula f of x is equal to x squared. Or a different function, the function f, which maps from the open interval from minus infinity to infinity, that's just the same as the real numbers, and has target closed interval from 0 to infinity, with the same formula, f of x is x squared. These two functions are different because they have different targets. We might think of a function like this. We start at the domain D and we map onto, or our function goes to a set y. If we start at x in D, the function takes us to a new point f of x, which is in y. If I start at the point t in D, the function takes us to the point f of t, and so on. We might not go on to all of y, we might go on to only part of y. The part that the arrows point at is called the range of f. Or we might think of a function as a machine. We put a number into the machine and we get another number out. We put a number x in the domain into the machine, and the number which comes out is the number f of x, which is in the target y. I'm going to run through some examples of some functions, and I'm going to talk about domains and ranges of these functions. First of all, the function y is equal to x squared. If we let x be any number between minus infinity and infinity, what are the possible values of y? And the answer is, if y is x squared, then y must be a positive number, a number between 0 and infinity. We can't get y equal to a minus number if x is a real number. Second line, y is equal to 1 over x. We could use every x in the real numbers except 0 because we can't do divided by 0. But then what would the range be? Let's think of some examples. Let's suppose we took x as 1. Then y would be 1 divided by 1 or 1. So 1 is in the range. I might have, let's say, x is 2, but then y is a half. So a half is in the range. I might take x is 100, but then y is 1 divided by 100. So 1 divided by 100 must be in the range. I could keep taking x bigger and bigger and bigger, and y would get smaller and smaller and smaller, but would not be 0. Or I might say, what about x is, let's say, a fifth. Y is 1 divided by x, so then y is 5. If x is 1 divided by 1,000,000, then y is equal to 1,000,000. So 1,000,000 must be in the range. We could do the same thing for negative numbers. If x is, let's say, minus 7, then y is minus 1 divided by 7. So minus 1 divided by 7 is in the range, and so on. Every number apart from 0 is in the range. Perhaps I should have written y here. Every number y in the real numbers except y is 0. Line 3, y is equal to the square root of x. What values of x could we use? We need to take the positive numbers because we can't take the square root of a negative number in the real numbers. And then what possible values of y do we make? Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and so on. We can get any number we want as high as we want just by choosing the correct x. We can't have that y is a negative number. So again, the range is going to be the closed interval between 0 and infinity. Now, line 4. Y is equal to the square root of 4 minus x. What is the biggest possible domain that we could use? Which values of x could we use so that this makes sense? I could use 4, I could use 3, I could use 2. These all make sense. If I use a number bigger than 4, though, let's say 5, I would have square root of 4 minus 5. We can't do that. The biggest number that we could use is x is equal to 4. What values could y take? Well, a square root is always positive, so we're not going to have any negative numbers here. Let's do some examples and see if we can work it out. If x is 0, y is the square root of 4 minus 0, which is 2. So 2 must be in this range. If x is 4, y is the square root of 4 minus 4 or 0? 0 must be in this range. What about if we go the other way? So let's say minus 5. Then y is the square root of 4 minus minus 5, square root of 9 or 3. We can go bigger and bigger, but we can't go smaller than 0. Y could take values between 0 and infinity. What about the domain of the next function? What is the biggest possible domain of the square root of 1 minus x squared? The answer is square bracket minus 1, 1 square bracket. So well done to 4 of you. To explain, if x is minus 1, we get square root of 1 minus minus 1 squared. That's square root of 0. That's fine. We can do that. We can do the square. If x is 0, we get the square root of 1. Not a problem. If x is 1, we get square root of 1 minus 1, square root of 0. Not a problem. But if x is bigger than 1 or smaller than minus 1, we would end up doing the square root of a negative number, which is not something we can do in the real numbers. So the biggest possible domain that we could use is square bracket minus 1 comma 1 square bracket. The range of this function is between 0 and 1. The smallest value we could get is 0 if we chose x is 1 or x is minus 1. And the biggest possible value we could get here is 1. That we would get that if we chose x is 0. Now, we don't have to always choose the biggest possible domain. We might want to restrict ourselves. So 3 different functions here. They're all y is equal to x squared, but I'm using different domains. Closed interval from 1 to 2, closed interval from 2 to infinity, or closed interval from minus infinity to minus 2. What are the ranges here? Well, we could have 1 squared, or we could have 2 squared. So between 1 and 4. If the domain is between 2 and infinity, what are the possible values of x squared? 2 squared is 4, and infinity squared is infinity, so we must be between 4 and infinity. But what's the next one? Let me set up a poll. One of these is the correct answer. Yes, most people are correct. Well done. And the final 2, y is equal to 1 plus x squared, with domain between 1 and 3. If x is 1, y is 2. If x is 3, then y is 10. So we must be between 2 and 10. Square bracket at 2, rounded bracket at 10. And the final one, y is equal to 1 minus the square root of x, where x is between 2 and infinity. If we choose x is 0, we get 1 minus 0, which is 1. If I chose x incredibly large, infinity, or some arbitrary large number, then we would get a negative arbitrary large number, or minus infinity. Graphs of functions. A graph of a function f is the set containing all of the points x, y, which satisfy the equation y is equal to f of x. For example, graph the function y is equal to 1 plus x squared over the interval from minus 2 to 2. The first thing I would do is I would make a table of x, y points which satisfy the equation. For example, if x is minus 2, y must be 5. If x is minus 1, y must be 2, and so on. Plot these points, and then draw a smooth curve through the points. Something like that is the best I can draw with my mouse. Now, I should point out not every curve that you can draw is a graph of a function. Remember that the value of a function is unique. For each x, there's only one f of x. That means that if we drew a vertical line on our picture, the vertical line can intersect the graph of a function at most one point. This tells us that a circle cannot be the graph of a function because some vertical lines, such as the one I've drawn, intersect the circle at 2 points. To say that again, if a is in the domain of the function, then the vertical line x equal to a will intersect the graph of f from d to I only at the point a, f of a. Next, I want to talk about piecewise defined functions. Sometimes we can use different formulae on different parts of the domain. For example, the absolute value function is defined to be equal to x if x is a positive number, but it's defined to be equal to minus x if x is a negative number. And the graph looks like this. Another example, we could define a function f of x to be minus x if x is negative, to be equal to x squared if x is between 0 and 1, or equal to 1 if x is greater than 1. And then the graph looks like this. We have a bit of minus x, a bit of x squared, and then a bit of 1. Increasing and decreasing functions. Let I be some interval, finite or infinite. F is called increasing on the function if the function's going up. F is called decreasing if the function is going down. In other words, it's increasing if whenever x2 is a bigger number than x1, f of x2 must also be a bigger number than f of x1. And for decreasing, we just change the first less than to greater than. For example, this function is always going up as we move to the right. This is an increasing function. This is a decreasing function. The function is always going down. And this function goes up, down, up, down, up, down, up, down. It's not always going up, so it's not increasing. It's not always going down, so it's not decreasing. We can classify functions as even or odd, or neither. Let me just remind you, the numbers 2, 4, 6, 8, and 10 are the even numbers. The numbers 1, 3, 5, 7, 9, etc. are the odd numbers. A function is called an even function, and here's the important part, if we always have the f of minus x is the same as f of x. The function is called an odd function if we have slightly different rule always being true. Function is odd if we always have that f of minus x is minus f of x. Some examples. The function x squared is an even function because if I start with f of minus x, that's minus x squared or x squared, which is the same as f of x. For this function, we always have the f of minus x is the same as f of x. So this function is called even. In terms of the pictures, we might imagine that we can put a mirror on the y-axis. And then the left part of the graph is a mirror image of the right part of the graph. X cubed is an odd function. If I start with f of minus x, that's minus x cubed or minus x cubed, which is the same as minus f of x. For this function, we always have that f of minus x is equal to minus f of x. So this function is an odd function. For an odd function, we can imagine taking the graph of the function and then rotating this graph 180 degrees about the origin. And we get exactly the same graph. Is the function x squared plus 1 even, odd, or neither? It's possible that the function is not even and is not odd. So let's try it out. The way we check it is we start with f of minus x. We go through the calculation and we get f of x. So this one must be even. What about g of x is x plus 1? Even, odd, or neither? Instead of looking at all x, I'm just going to look at some numbers. I'm just going to look at g of minus 2 and g of 2. G of minus 2 is minus 1, g of 2 is 3. So g of minus 2 is not the same as g of 2. This function is not even. G of minus 2 is not the same as minus g of 2. This function is not odd. This function is neither even nor odd. Before I go on, let me remark, if we want to prove the function is even or is odd, we need to prove that the equation is true for every x. So we need to start with f of minus x and then see what we get. If I'm trying to show that a function is not even, is not odd, I don't need to do it for every single x. I just need to find one number where the rule fails. The opposite of always being true is at least one point is false. Now let's run through some common types of functions. The linear functions are the functions where the graphs are straight lines. Functions of the form mx plus b for numbers m and b. I'm going deliberately very, very quickly now, but tell me in the chat if you want me to slow down. Power functions are the functions x to the power of a, where a is a real number. For example, y is equal to x, a is 1 here, x to the power 1, x to the power 2 or x squared, x to the power 3 or x cubed, x to the power 4, etc. We could also use minus numbers, negative numbers. X to the power minus 1 is the same as 1 over x. We could use fractions. X to the power of a half means square root of x. Or cubed root of x, x to the power 1/3. X to the power 3 over 2. X to the power 2 over 3. And so on. Functions like this are called polynomials. There's a number, an, and then a power function plus number, power function plus number, power functions, etc. The domain of a polynomial, by which I mean the biggest possible domain of a polynomial, is always the whole real line. If we do polynomial divided by polynomial, we get a function which is called a rational function. For example, 2x cubed minus 3 divided by 7x plus 4. That's polynomial divided by polynomial. That is a rational function. Functions of the form a to the power x, where a is a real number, a is a positive number, and a is not 1, are called exponential functions. And the graphs look like this. If a is a number which is bigger than 1, then the exponential function will curve up. If a is a number which is between 0 and 1, like this red curve, we will get a graph which goes downwards. The logarithmic functions are the inverses of the exponential functions. We say that y is log base a of x if and only if x is equal to a to the power y. And again, a is a real number, a is a positive number, and a is not 1. Compare this graph with the one on the previous page. You'll see that one is just the other graph flipped over. We need to talk about angles. We're going to need this later in the course. There's two ways to measure angles. We can use degrees or we can use radians. I want to talk about radians now. The way that radians work is, imagine we have a circle of radius 1. And let's suppose I want to measure the angle between these two lines. Then what we do is we measure the distance around the outside of the circle, and this is the size of the angle in radians. On the right-hand side, I've drawn a semicircle. We know that the angle inside a semicircle is 180 degrees, and we know that the distance around the outside of a semicircle of radius 1 is pi radians. So 180 degrees must be the same as pi radians. Divide by pi, that's the same as saying 1 radian is the same as 180 divided by pi degrees, or 1 degree is the same as pi divided by 180 radians. I've drawn 3 common angles at the bottom. When we measure an angle using degrees, we need to put a little circle to say that we're using degrees. When we use radians, we don't put any symbols. 45 degrees is the same as pi over 4 radians. 60 degrees is the same as pi over 3. 90 degrees is the same as pi over 2. Now in calculus, we have to use radians. Part 2 of this course is about geometry. In geometry, you can use whichever one you want. You can use degrees if you want, you can use radians if you want in geometry. But when we get to part 4 of this course, when we're doing calculus, we have to use radians because calculus doesn't work if we use degrees. The trigonometric functions. Let's suppose we have a circle. We have a point on the circle with coordinates x and y. And let's suppose we measure the angle between the x-axis and the ray from the origin through the point xy. And I'm going to suppose that this circle has radius r. The sine function is defined to be sine theta is y divided by r, and cosine theta is defined with cos theta is x over r. After we have these two, we can use these to define the other 4. Tan means sine divided by cos. Secant, sec, means 1 divided by cos. Cosecant, 2 ways to write cosecant. You can write cosec or you can write csc. This means 1 divided by sine, and cotangent or cot means 1 divided by tan. Now, just to be careful, these are only defined as long as we're not dividing by 0. So tan and sec are only defined as long as cos theta is not 0. Cosec and cotan are only defined as long as sine of theta is not 0, because we don't want to be doing divided by 0. I have here a right angle triangle of height and base 1. By Pythagoras, the other side must be root 2. The angles are pi over 4 or 45 degrees and pi over 2 or 90 degrees. From this triangle, we can read off that sine 45 degrees or sine pi over 4 is 1 over root 2. That's 1 divided by root 2. Cos 45 or cos pi over 4 is 1 divided by root 2. And then after we have those two, we can get the other 4. Tan means sine divided by cos, sec means 1 divided by cos, cosec means 1 divided by sine, and cotan means 1 divided by tan. Another common one. Let's suppose we start with an equilateral triangle of side 2 and then chop this in half. Then I have a triangle of base 1, hypotenuse 2, and by Pythagoras, the other side must be root 3. The angles inside are pi over 3, or 60 degrees, and pi over 6, or 30 degrees. I'm interested in this angle, pi over 3, or 60 degrees. Sine 60, or sine pi over 3, is root 3 divided by 2, height divided by hypotenuse, and cos 60 degrees or cos pi over 3 is base divided by hypotenuse, so 1 divided by 2. And then after you have those, you can use those to get the other 4. The graphs of sine and cosine look like this. The graphs which go up, down, etc. Sine passes through the origin because sine of 0 is 0. Cosine of 0 is 1. So it passes through this point 0, 1. And that brings us to the final chapter of today's lesson. Very, very quickly, I want to talk about sigma notation, which we would need later in the course. If I wanted to do number plus number plus number plus number plus number, for example, A1 plus A2 plus A3 plus A4 plus A5 plus A6, etc. There's an easier way to write this. Instead of writing this long thing out, I could use sigma notation. This symbol is capital Greek letter sigma. And what this means is we have a sum which starts at k equal to 1 and it finishes when k is equal to n. So we start with A1 and we finish with AN. For example, 1 squared plus 2 squared plus 3 squared plus 4 squared, all of the way up to 11 squared. We can write this as sigma, or sum, from k is equal to 1 to 11 of k squared. F of 1 plus f of 2 plus f of 3 plus dot 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 plus f of 99 plus f of 100. I could write this as the sum from 1 to 100 of f of k. Or the sum from 1 to 5 of k. This means 1 plus 2 plus 3 plus 4 plus 5, which is 15. The sum from 1 to 3 of minus 1 to the power k, k. I'll leave this for you to check. We get minus 2. The sum from 1 to 2 of k over k plus 1. We start using k is equal to 1, so that's 1 over 1 plus 1. And then we go to k is equal to 2, 2 over 2 plus 1. And then we finish, because 2 is at the top. We don't have to start at 1. So far I've been starting with k equal to 1, but we don't have to. We could start at any number we wanted. For example, the sum from k is equal to 4 to 5 of k squared over k minus 1 is 4 squared over 4 minus 1 plus 5 squared over 5 minus 1. I want to find a formula for 1 plus 2 plus 3 plus 4 plus 5 plus ... plus n. And actually, I'm going to start with 2 times this. 2 times 1 plus 2 plus 3 plus 4. I have one lot, 1 plus 2 plus 3 plus 4 plus 5, and I have another lot. For the second lot, I'm changing the order. 1 plus 2 plus 3 plus 4 plus 5, etc. is the same as 5 plus 4 plus 3 plus 2 plus 1. So changing the order around. And then I'm looking at numbers which are above each other. One plus n is n plus 1. 2 plus n minus 1 is n plus 1. 3 plus n minus 2 is n plus 1. 4 plus n minus 3 is n plus 1. Look what we have. We have n plus 1 plus n plus 1 plus n plus 1 plus n plus 1 plus n plus 1, etc. How many of these do we have? We have n of them. N multiplied by n plus 1. Divide by 2, and we have the formula that we want. The sum of the first n natural numbers is n multiplied by n plus 1 divided by 2. We have similar formulae for the sum of the first square numbers and the first cubic numbers, but these are a little bit more difficult to prove. We will need these formulae later as well. And that brings me to the end of today's lesson. I've deliberately talked quickly this week. In future weeks, I will talk more slowly. Do you have any questions?